So, welcome to my dear student. So today I am going to discuss some important topic on digital and data communication. So for that, whenever we are transmitting any analog signal in a digital form, so the first job is that the data is to be sampled with in some interval. Okay, so let us just go back to some earlier concept of Fourier series expansion. So let us take one. So this is your time axis and there are some impulse function. Okay, so those are the impulse functions. Like this. So say in the time axis this is 0, this is TS, this is 2TS, this is 3TS, and similarly this is minus TS, this is minus 2TS, and so on. Now if I represent this function in a form of infinite series, which is Fourier series, then first I have to calculate. So this impulse function is getting repeated in every TS time, so that is the period. So the A0 is nothing but, so this is an impulse function. Okay, so A0 is nothing but 1 by TS integrate minus TS by 2 to TS by 2 del T dt. Okay, but this impulse function only exists at t is equal to 0. So and that value become 1. So this value naturally it is 1 by TS. Okay, similarly if we find the value of an, so what is an? This my del T into cos n omega s t dt. Okay, so naturally this function also it will exist at t is equal to 0. So at t is equal to 0, sorry, this will be Ts by 2 or it will be 2 by Ts. So this will be converted to again 1, because at t is equal to 0 del t 1 and t is equal to 0 cos 0 1. So this will be like this. And for Bn, instead of this cos function, there will be sine function, and similarly that also will exist at t is equal to 0. So t is equal to 0, sine 0 becomes 0, so Bn part will become 0. Okay, so my a0 is 1 by ts and my an is 2 by ts and Bn is 0. Now if I represent this function in an infinite series, then say I am representing this all as del s t. So that can be represented as a0 by 2, which is 1 by ts, and then plus summation n is equal to 1 to infinity an value is 2 by ts cos n omega s t. Am I right? So this is the Fourier series expansion of the function which is shown here. Okay, now let us take one message signal. Say it is like this. This is a message signal, and here also I am sampling, I am capturing the value of this message signal at same instant where this del s function, wherever the impulse functions are there in the del s. So like this. So let us take this function. This is the information function or the message signal. Let us take mt. Okay. Now if we multiply these two signal, okay, so what it will come means I am trying to find out this mt into del st. Okay, this I am trying to find out. So that means what this means? This means that this, the value of mt, the signal mt, it is sampled at the time interval of ts. It means that. Okay, so that will become, so this entire this function will be multiplied by mt. So the first, so I am taking common 1 by ts, then the first term will be mt, and the second term will be 2mt cos omega nst, cos omega st. The third term will be mt cos omega st and so on till infinity. Okay. Now if I try to, and let us consider, once this time domain message signal it is transferred to frequency domain, the Fourier transform whatever we will get, let us assume that is m of omega. That means your message signal it was like this, and once it is converted from time domain to frequency domain, so it may look like, say, something like this. Okay, so there is the frequency here started with -b and the spectrum exists till +b. So within this range, this frequency, this spectrum exists. Okay. So now if we take the Fourier transform of this function, so what it will come? So you see, this will be, so let us take this function is gt. Gt is equal to mt into del st. Now if I take the Fourier transform of this gt and let us assume it is g omega, what it will come? 1 by ts then this mt is Fourier transformed by m omega, and these things mt into cos omega st, that means 2 cos a cos b, one term it will come, so that will be cos a plus b into cos a minus b. So one term it will come m omega plus minus omega s, then the third term, this term, it will come m, this is the frequency shifting property. And this will come omega plus minus 2 omega s, and so on. So if I write this Fourier transform g omega in a simplified form, so what it will come? This g omega I can write 1 by ts summation minus infinity to plus infinity g omega plus minus n omega s plus minus n omega s. Okay, these things it will come. That means, what it means, that in the frequency domain, so if this is the frequency is 0, then at every omega s the spectrum will exist. Okay, every omega s. So this is your center this is 0, so this is omega s, this is 2 omega s, 3 omega s, minus 2 omega s, and so and so. So already we have seen the spectrum of g omega. Say it looks something like this. So again the next spectrum will be placed here, and the next will be placed here, and so on, so on. So this message signal MT, which was that message signal was, and this spectrum was limited, it's a band limited by B hertz in picture. So that means band limited by B hertz means this is B and this is minus B. Fine. And here also this is omega s plus B, and this point omega s minus B, like that. So absolutely in this case there is no problem if we try to reconstruct the signal. Now take another condition. Say now my picture is like this. Okay, so now let us take another condition. So this is same, this is omega s, 2 omega s, and so on. So now let us take another condition. It is like this. So this kind of situation is arising. That means what I mean to say, that this area are getting overlapped. So if this type of condition is arising, then from this kind of situation you cannot reconstruct the signal. So at least the spectrum of the message signal, it will be just touching each other or it will be away. Okay, suppose the spectrums are like this. Say this is also good, absolutely no problem. But if it is coincided or overlapped with each other, this condition is not at all satisfactory to reconstruct the signal, because some area is getting overlapped, the data will lose, some distortion will come, this kind of problem it will come. So at least, so now you see this is my 0 and this is my omega s, and so this should be my omega s. So this is my, this point is omega s by 2, and this point is minus omega s by 2. Okay, so that means if you compare this, because this my GT is band limited to B, so my omega s by 2 that is equal to B, or my omega s is equal to 2B. Omega, if you take omega, then it is to be multiplied by 2 pi. B is in terms of frequency, so whatever may be. So now you see, so from this condition, this analysis, this mathematical analysis, we understood that for successful reconstruction from a sample data, the sampling rate at least should be equal to 2B or higher than that. If it is 2B, exactly 2B, then it will be like this. If it is higher than 2B, it is like this. And if it is less than 2B, it is like this. So for successful reconstruction, the minimum requirement, the sampling rate should be at least equal to 2B or higher than that. Okay, so now my sampling time interval Ts, that should be, so it will be opposite to, so what I mean to say, this my omega s should be greater than equal to 2B, or my sampling interval Ts should be lesser than at least 1 by 2B. This is a very important in digital communication, and this condition is called the sampling theorem in communication system. So I hope all you have understood the concept of sampling theory. This is called the sampling theory. Okay, so once again I am telling you the gist. If a signal, if the spectrum of a signal is band limited to B hertz, okay, then the signal can be reconstructed exactly without any error if it is sampled at least at a rate of 2B hertz or 2B samples per second. Otherwise it is not possible. So again I am telling, if the signal is, the spectrum of the signal is band limited to B hertz, then the sampling rate at least should be 2B or higher than that. So hope it is you understood the concept. Thank you so much.